Good evening and welcome back. Wherever you are and whatever kind of day is finally letting go of you, I'm glad you're here. Maybe you've pulled the blankets up to your chin. Maybe you're lying in the dark with one lamp still glowing softly in the corner, or resting your eyes on a long journey home. However you've arrived, there's nothing you need to do for the next little while but breathe slowly, loosen your shoulders, and let the world grow quiet around you. Before we begin, I'd love to know one small thing. What corner of the world are you drifting off in tonight? People find their way to these quiet recordings from every kind of place. A city apartment with the traffic humming far below. A farmhouse where the only sound is the wind. A bunk on a train slipping through the dark. A room where the sun has only just gone down, and another where it rose hours ago. If you feel like it, you might leave a little note further down to say hello and where you are. There's something wonderfully calming about the thought of so many people, scattered across the whole turning planet, all settling in under the same quiet stars. And if these slow, gentle explorations help you unwind, a soft tap of the like button and a quiet subscribe genuinely help more than you'd think. Channels like this one are small, and they only grow when a few kind listeners decide to stay a while. Every like is a small signal to the machinery behind the curtain that this calm little corner is worth showing to someone else who can't quite sleep. Every subscription is a gentle vote that says, please keep making these. It costs you nothing, it takes only a moment, and on this end it means the world. So thank you truly, whether this is your first night here or your 100th. Now, a soft word about where we're going tonight. Last time, on our slow journey together, we shrank ourselves down smaller and smaller into the strange and shimmering world of the very small, where a single particle can behave like a spread out wave, and nothing is quite certain until it's looked at. Tonight, we turn around completely and travel to the opposite extreme. We're going to fall, ever so gently, toward the heaviest, darkest, most extreme objects the universe has ever built. We're going to ask a question that has kept some of the cleverest people alive lying awake at night. What on earth happens inside a black hole? I promise there will be no mathematics to wrestle with, no formulas to memorize, and no test waiting at the end. If anything, my hope is the exact opposite of a physics lecture. I want to take the strangest, most dramatic ideas in all of science and turn them soft, almost like a bedtime story, so you can follow along in a warm, drowsy, half-dreaming sort of way. And if you happen to fall asleep somewhere in the middle, long before we reach the center, that isn't a failure at all. That's precisely what this is for. Consider it the highest compliment you could pay me. Here's what I find so beautiful about black holes. They sound like the most frightening things imaginable, cosmic pits that swallow everything and never give it back. And yet, when you look closely, they turn out to be some of the most elegant and surprising objects in all of nature. Places where the very ideas of space, of time, and of what is possible bend and soften in ways that feel almost like poetry. They are not really holes, and they are not really empty. They are something far stranger, and in their own way far gentler than their fearsome name suggests. So tonight, we're going to take our time. We'll start far away, in the safety of ordinary space, and drift slowly inward, one careful step at a time. We'll ask how these things are even made, what waits at the edge, what would happen if you fell in, and what, if anything, lies at the very heart. Along the way, we'll meet collapsing stars, frozen clocks, a faint glow that shouldn't exist, and the ghostly ripples that finally let us hear two of them collide. So settle in, close your eyes if you'd like, and let's begin our slow fall toward the darkest and most wonderful mystery in the sky. Before we can understand a black hole, we have to spend a little time with the thing that makes one, gravity. And gravity, it turns out, is not quite what most of us are taught to imagine. When we're young, we're often told that gravity is a kind of invisible pull, a force reaching out from the earth, tugging apples down from trees and keeping our feet on the ground. That picture works well enough for everyday life. But a little over 100 years ago, a patient thinker named Albert Einstein offered a deeper and stranger way of seeing it, and that new way is the key that unlocks everything we're about to explore. Einstein's idea was this: space is not just an empty stage on which things happen. Space itself, together with time, is more like a vast, smooth, invisible fabric that can bend, stretch, and sag. And anything with mass, anything made of stuff, presses into that fabric and shapes it. The heavier the object, the deeper the dip it makes around itself. Now, the usual bedtime image people reach for is a heavy ball resting on a stretched sheet. But let me offer you a gentler one to rest on tonight. Picture a wide, still pond on a windless evening, its surface perfectly calm. Now imagine that space, very quietly, is always drifting, flowing slowly inward toward anything heavy, like the faintest current in that pond, gliding toward a place where the water sinks away. A pebble sitting in the pond barely stirs it, but something enormous, something dense, pulls the whole surface toward it in a slow, endless drift. What we feel as gravity in this picture is simply us being carried along by that gentle inward flow of space. The earth isn't reaching up and grabbing you. The earth is dimpling the space around it, and you are quietly sliding down that dimple, held against the ground by the softest of cosmic currents. It's a calmer thought than a tug of war, isn't it? Nothing is pulling. Everything is simply drifting downhill, along the shape that mass has carved. For most objects, this dip in space is shallow and mild. The sun makes a broad, gentle valley, and the planets roll around its rim like marbles, circling a wide bowl, never quite falling in. The Earth makes a smaller dip, and the moon circles that. Even you, right now, are making the tiniest dimple in the fabric of space, far too faint to ever notice. Gravity, in this view, is not a force so much as a shape, the shape that stuff gives to the emptiness around it. But here is the question that leads us, step by step, toward the darkness. What happens if you take a great deal of matter and squeeze it into a smaller and smaller space? The dip grows deeper. The inward current flows faster. Pack enough mass tightly enough, and that gentle valley steepens into a slope, and the slope steepens into a cliff, and the calm inward drift of space becomes a rushing, headlong plunge. Squeeze matter enough, and space itself begins to pour inward so quickly that nothing, not even light, the fastest thing there is, can climb back out. That is a black hole. Not a thing, really, but a place. A place where space has folded so steeply around a concentration of matter that it has closed off a little region of the universe from the rest, sealing it away behind a one-way current. Everything we explore tonight flows from this single idea, that gravity is the shape of space, and that if you bend that shape sharply enough, you can tear a quiet, permanent hole in the fabric of the sky. So the real question isn't quite what is a black hole. It's how do you bend space that far? And for that, we need to visit the most reliable black hole factories in the universe, the stars. It's worth pausing before we fall any deeper to remember that black holes were, for a very long time, an idea that almost nobody took seriously, including many of the greatest scientists who helped invent it. Their story is a lovely reminder that even the most solid-seeming facts about the universe often begin as ideas so strange they seem faintly ridiculous. The first faint whisper of the idea came surprisingly early, more than 200 years ago, from an English clergyman and natural philosopher named John Michell. Working in the 1780s, long before anyone understood what light truly was, he wondered, if gravity can pull back a ball thrown into the air, could there be a star so massive, its gravity so strong, that not even light could escape it? He imagined what he called a dark star, a sun so heavy it would be invisible, its light forever unable to leave. A French thinker, Pierre-Simon Laplace, mused along similar lines a few years later. It was a remarkable guess, centuries ahead of its time. And then, for the most part, the idea was quietly set aside and nearly forgotten. It stirred back to life in the 20th century, and in the unlikeliest of places. In 1915, Einstein had just unveiled his great new picture of gravity as the bending of space and time. Only months later, a German physicist named Carl Schwarzschild worked out one of the first exact solutions to Einstein's equations, describing the space around a perfectly round mass. And he did this astonishing piece of work while serving as a soldier on the Eastern Front of the First World War, calculating amid the mud and thunder of the trenches. Tucked inside his solution was something troubling, a particular distance from the center where the mathematics seemed to misbehave, where the numbers ran off to infinity. That distance, we now know, was the event horizon. But at the time, almost no one, Einstein included, believed it described anything real. Surely, they thought, no true object could ever actually be crushed down small enough for this to matter. Surely nature would find some way to prevent it. For decades, the idea lingered in this uncomfortable limbo, mathematically possible, but widely dismissed as a curiosity that could never really happen. Einstein himself once wrote a paper arguing that such objects could not form. Even the name we use today didn't exist. These things were referred to only by clunky technical phrases, as though no one wanted to grant them a proper title. It wasn't until 1967 that the American physicist John Wheeler helped popularize a short, stark, unforgettable phrase for them, black holes. And with that simple name, the idea finally took hold in the imagination and never let go. What truly changed people's minds, though, was a mix of beautiful mathematics and stubborn evidence. In the 1960s, a brilliant thinker named Roger Penrose proved something remarkable, that under very general conditions, Einstein's own theory of gravity does not merely permit black holes, it demands them. If enough matter collapses, the formation of one of these dark regions is not a fluke or a special case, but an almost inescapable consequence of the way gravity works. This was such a profound insight that, half a century later, it would earn him a share of the highest prize in physics. And around the same time, astronomers found their first strong real-world suspect, a source of powerful, flickering energy in the sky, where a visible star appeared to be circling something heavy and unseen, something small and dark and hungry. It looked, for all the world, exactly like a star being slowly devoured by an invisible companion. The evidence mounted, decade after decade, from suspicion to strong hint to near certainty, until at last, in our own time, we felt the ripples of two black holes colliding and even captured a photograph of one's shadow. The dark stars that a country clergyman dreamed of 2 centuries ago, that the greatest minds of the 20th century found too strange to believe, turned out to be scattered across the whole universe, and even to be sitting quietly at the very center of our own galaxy. I find that a wonderfully hopeful thought to rest on. The next time you hear an idea about the universe that sounds too strange to be true, remember the black hole, dismissed, doubted, and set aside for the better part of 200 years, and real all along. Almost every black hole scattered through the sky began its life as something radiant and warm, a star. To understand how something so bright becomes something so dark, we have to understand what a star really is, because a star, for all its glory, is a balancing act that cannot last forever. Think of a star as a constant, quiet struggle between 2 opposing wishes. On one side, there is gravity, forever trying to pull all that enormous mass inward, to crush the star down toward its own center. On the other side, there is heat and pressure, pushing outward, trying to make the star swell and spread. Deep in the core of a star, under crushing pressure, the smallest pieces of matter are forced together so violently that they merge and release tremendous energy. The very same process that makes our sunlight. That outpouring of energy pushes outward and holds the star up, propping it open against the relentless inward pull of its own weight. For most of a star's long life, these 2 forces stay in near-perfect balance. The outward push of its burning core exactly cancels the inward pull of gravity, and the star shines, steady and calm, for millions or billions of years. Our own sun has been holding this balance for around 4.5 billion years, and it has a good while yet to go. But no star has an endless supply of fuel. Sooner or later, the core runs low. The fire in the middle begins to fade, and the moment the outward push weakens, the long-held truce breaks, and gravity, which has been waiting patiently this whole time, finally begins to win. What happens next depends entirely on how heavy the star was to begin with. A modest star like our sun will, in its old age, gently shrug off its outer layers and settle down into a small, dense, slowly cooling ember about the size of the Earth. It's a quiet, dignified ending, and it makes no black hole. But the giants, the truly massive stars, many times heavier than the sun, meet a far more dramatic fate. When the core of one of these giants finally gives out, there is nothing left to hold it up, and gravity seizes it all at once. In a fraction of a second, the core collapses inward, faster than you can imagine, and the outer layers come crashing down behind it. The result is one of the most violent events in all of nature, a supernova, a single dying star briefly blazing brighter than an entire galaxy of ordinary suns, scattering the ingredients of new worlds out into space. And yet, even as the star's outer layers are blown outward in that brilliant flash, the very heart of it keeps falling inward. If the collapsing core is heavy enough, very roughly, if what remains is more than about 2 or 3 times the mass of our sun, then nothing known to physics can stop it. Not the stubborn resistance that holds up an ordinary star, not the even fiercer resistance that props up the ultra-dense cinders we call neutron stars. Nothing. Gravity simply keeps squeezing, and the core keeps shrinking, smaller and smaller and smaller, its dip in the fabric of space growing ever steeper, until it seals itself away behind that one-way current we spoke of. In that instant, a black hole is born. Where a magnificent star once burned, there is now a region of space so steeply folded that light can no longer escape it. the star hasn't been destroyed exactly. It has been folded away, hidden behind a horizon, its immense mass still very much present, still bending the space around it, but now utterly invisible. It's a strange and rather moving thought to drift on. The blackest things in the universe are the corpses of the brightest. Every black hole born this way is a monument to a star that once poured its light across the cosmos for millions of years, and then, at the very end, fell so completely inward that it took its own light with it. Death, out here, is not an ending so much as a folding shut, a closing of the curtain so total that no light ever finds its way back through. But what, exactly, is that curtain? What is this edge, this horizon, beyond which everything falls and nothing returns? That is where we go next. Every black hole is wrapped in an invisible boundary, and that boundary has a name that sounds almost poetic: the event horizon. It is one of the strangest ideas in all of science, and once you understand it, black holes stop being frightening and start being genuinely fascinating. Let's return to our image of space as a gently flowing current, drifting inward toward anything heavy. Far from a black hole, that current is a mere trickle, the soft, familiar pull we call gravity. But as you drift closer to a black hole, the current quickens. Closer still, and it becomes a stream, then a river, then a torrent, pouring inward faster and faster. Now, imagine a swimmer in that river, and let that swimmer be a ray of light, the fastest traveler in the universe. Light always moves at the same tremendous speed, whether it's the glow of a distant star or the beam of your bedside lamp. Nothing outruns it. So picture this beam of light swimming outward, away from the black hole, paddling against the inward current with all the speed nature allows. Far out, where the current is gentle, the light wins easily. It swims upstream and escapes into the wider universe. And this is why we can see the stars, the galaxies, the glow of almost everything in the sky. But as our light swimmer ventures closer to the black hole, the inward current grows stronger, and the going gets harder. There comes a place, a particular distance from the center, where the current is flowing inward at exactly the speed of light itself. Right there, our swimmer, paddling outward at top speed against a current rushing inward at that same speed, makes no progress at all. It hangs, frozen, at the edge, running as fast as it possibly can and going precisely nowhere. That place, that invisible spherical surface, where the inward flow of space finally matches the speed of light, is the event horizon. It is the point of no return. Step even a hair's breadth inside it, and now the current is faster than light. And since nothing in the universe can move faster than light, nothing can swim back out. Not a beam of light, not a spaceship, not a whispered message, not you. Once you cross that line, every possible path, every direction you could ever travel, leads deeper in. Escape isn't just difficult. It becomes as impossible as traveling backward into yesterday. This is the key to the whole mystery, so let me say it as softly and clearly as I can. The event horizon is not a wall. There is nothing there to touch, nothing solid, no shimmering barrier. If you fell through it, you might not notice anything special at that exact moment at all. It is simply the line beyond which the universe has tilted so completely inward that out is no longer a direction that exists. It is less like the edge of a cliff and more like the crest of a waterfall, a smooth, silent place past which the water was always going to fall, whether it meant to or not. And here is something that surprises almost everyone. The event horizon can be astonishingly small. A black hole with the mass of our entire sun, all that fire and fury, all that unimaginable weight, would have an event horizon only about 3 kilometers from its center to its edge. Not 3,000. 3. The whole thing would fit comfortably inside a small town. A black hole as heavy as the entire Earth would be no bigger than a marble. The mass is enormous, but it's the squeezing, the sheer concentration that matters. Black holes are the universe's way of taking something huge and folding it into almost nothing at all. So the event horizon is the true edge of a black hole, not a surface, but a threshold, a place where the map of here and there quietly rearranges itself so that every road leads inward. Everything else we talk about tonight lies on the far side of that line. And now that we've found the edge, there's only one thing left to do, the thing you've probably been wondering about since we began. We have to go over it. We have to fall in. Let's do something no one has ever actually done and lived to describe. Let's fall into a black hole together, gently, in our imaginations, and see what it would be like. Don't worry. We'll only be visiting in the mind, and we can drift back out whenever we please. Suppose you're falling feet first toward a black hole from far away. At first, the fall feels like nothing at all. This is one of the quiet secrets of falling. When you're in free fall, you feel weightless, floating, peaceful. There's no rushing wind out in the vacuum of space, no sense of speed. You could close your eyes and imagine you were simply hanging still while the black hole drifts silently up to meet you. But as you draw closer, something begins to change, and it comes from a simple fact. Gravity is always a little stronger, the closer you are to whatever's pulling you. Near a black hole, this small difference becomes dramatic. If you're falling feet first, your feet are closer to the black hole than your head, and so your feet feel a noticeably stronger pull than your head does. Your feet are tugged downward harder, your head held back a touch more gently, and the difference begins, ever so slightly, to stretch you. Physicists have given this stretching a rather whimsical name for such a serious business. They call it spaghettification. As you fall further in, the difference in pull between your feet and your head grows and grows until you are drawn out longer and thinner, like a single slow thread of honey trailing off a spoon, or a piece of warm taffy pulled gently at both ends. For a small black hole, this stretching would become uncomfortable and then overwhelming, long before you ever reach the center. It is not, perhaps, the most restful image, so let me offer you a kinder one. For the truly enormous black holes, the giants we'll meet later tonight, the stretching near the edge is so mild that you could cross the horizon and feel almost nothing at all, drifting across the point of no return as smoothly as slipping beneath the surface of a warm bath. And that is the strangest part of falling in. If you cross the horizon of one of those giant black holes, there would be no fence, no flash, no alarm, no moment where the universe announced, "You have now passed the point of no return." You would sail across that invisible line in perfect silence, feeling nothing unusual, still able to see the stars behind you. And yet, in that quiet instant, your fate would be sealed. Every direction you could now choose would lead inward. You could fire the most powerful engine ever built, point it straight back toward the stars, and still drift ever deeper. The universe outside would carry on without you, and you would have no way to ever send word back across the line. There's something almost peaceful in that, if you don't think too hard about it. The most dramatic boundary in all of nature is crossed without a sound. No struggle, no fanfare. Just a smooth, silent slipping over. From a universe you could always leave into one you never can. Now, from your own point of view, falling inward, the journey would continue. You'd fall on, down toward the center, in what feels to you like a short, quiet plunge. And this is where black holes begin to play their deepest tricks. The story looks utterly different to someone watching you from far away. To them, you would never seem to cross the horizon at all. To them, something impossible and haunting would appear to happen to time itself. And time, as it turns out, is where black holes become truly strange. So let's slow down and talk about what happens to a clock as it falls toward the dark. We tend to think of time as the one thing we can count on. A second is a second, everywhere and always, ticking along at the same steady pace for everyone. But one of the great discoveries of the last century is that this simply isn't true. Time is far more flexible, far more personal than it feels. And nowhere does it bend more dramatically than near a black hole. Here is the strange truth, as gently as I can put it. The stronger the gravity around you, the more steeply space is folded, the more slowly your time flows compared to someone far away in gentler surroundings. This isn't a trick of the mind or a fault in the clocks. It is time itself, running at different speeds in different places. Down in a deep gravitational valley near a heavy object, every clock ticks more slowly. Your wristwatch, your heartbeat, the aging of your very cells. And the deeper the valley, the slower it all goes. Near the surface of the Earth, this effect is real, but almost absurdly tiny. Clocks on the ground run just a hair slower than clocks high up on a mountain or aboard a satellite. It's a difference of the smallest slivers of a second, spread over years, far too small to feel. And yet it is genuine. And the satellites that guide us across our cities have to account for it, or they would slowly lead us astray. But near a black hole, where space is folded almost to breaking, this gentle effect becomes overwhelming. So let's return to our imagined fall, but this time, let's split into two. Imagine you fall toward the black hole while a dear friend stays safely behind, watching you through a telescope from far away, holding a bright lantern so you can see them too. As you fall toward the horizon, your friend, watching from afar, sees your time begin to slow. Your falling seems to ease, as though the whole scene were drifting into slow motion. And it gets stranger. The light coming from you, say the glow of your own lantern, takes longer and longer to climb back out of the deepening gravity and reach your friend's eyes. Your lantern's light stretches, shifting from white toward red, then toward deep red, growing dimmer and dimmer. To your friend, you appear to slow and redden and fade, drifting closer and closer to the horizon, but never quite reaching it. You seem to hang there, frozen at the edge, growing ever fainter, until at last your light stretches beyond what any eye or instrument could catch, and you simply melt into darkness. From the outside, you never cross the line. You are frozen at the threshold, a fading after-image on the very edge of the dark. And yet, and this is the tender heart of it, from your own point of view, nothing of the sort happens. You feel no slowing. Your watch ticks normally. Your heart beats at its usual steady pace. You sail smoothly across the horizon in a moment, exactly as we described, and continue your fall inward. The freezing was never something that happened to you. It was only ever how your journey looked to those you left behind. Sit with that for a moment, in the quiet. Two people, watching the same fall. To one, it takes an eternity and never quite finishes. To the other, it's over in a heartbeat. Both are completely correct. There is no single true answer to the question, how long did it take? Because near a black hole, time itself stops being one shared river and splits into separate streams, each carrying its own traveler at its own pace. This is one of those ideas we'll return to on another night, when we take a whole slow journey into the question of what time really is. For now, let it simply wash over you. Near a black hole, the steady ticking we build our lives around comes quietly undone. But before we let ourselves fall all the way to the center, there's one more surprising thing worth noticing about the black hole itself. Something that makes these the most fearsome objects in all the universe, in a strange and precise way, also the very simplest. Here is something that surprises almost everyone. For all their mystery, black holes are, in one very precise sense, among the simplest objects in the entire universe. And that simplicity is itself one of the strangest things about them. Think about how much there is to say about an ordinary object, a stone, a planet, a person. To describe it fully, you would need to know its shape, its color, its temperature, what it's made of, how its countless atoms are arranged, every scratch and freckle and detail. Something like the Earth holds an essentially endless amount of information within it. But a black hole is different. Once something has fallen behind the horizon, all of that rich detail vanishes from view. And it turns out that, from the outside, a black hole can be completely described by just a tiny handful of numbers, really only 3. How much mass it has, how fast it is spinning, and whether it carries any electric charge, which in practice is almost always essentially none. That's all. 2 black holes with the same mass and the same spin are utterly, perfectly identical, no matter what they were made from. One could have formed from a collapsing star, and another from an unthinkable heap of old books and cold coffee and worn-out shoes. And if their mass and spin matched, there would be no way ever to tell them apart. Everything else about whatever fell in, all its color and complexity and history, is hidden away behind the horizon. Physicists sum this up with a wonderfully whimsical phrase. They say that black holes have no hair, meaning they have no extra features, no distinguishing marks, nothing but those few bare numbers. It's a strange kind of purity. The most extreme objects in the universe are also, from the outside, the most featureless and plain. Now, of those few numbers, the one worth lingering on tonight is the spinning, because black holes very much do spin, and most of them spin fast. Remember that black holes are usually born from collapsing stars, and stars turn. As a great star collapses, that turning doesn't disappear. It gathers and speeds up, the same way a spinning skater whirls faster when she pulls in her arms. So by the time a star has folded down into a black hole, its spin can be tremendous, its horizon whirling around at a fair fraction of the speed of light. And a spinning black hole does something truly remarkable to the space around it. It doesn't just fold space inward. It grabs the very fabric of space and drags it around with it, like a spoon slowly stirring thick honey, winding everything nearby into the same swirling motion. Close to a spinning black hole, there is a region where space is being pulled around so relentlessly that nothing could possibly hold still, no matter how hard it tried. Even a beam of light, even you, would be swept helplessly along in the direction of the spin, carried around and around, unable to stand in one place. Not because anything is pushing you, but because the very ground of space beneath you is turning like a great, silent whirlpool. This whirlpool of drag space sits just outside the point of no return, and it's a genuinely strange place, a region where you'd be forced into motion by the turning of space itself, and yet could still, in principle, escape back out to the wider universe, so long as you hadn't crossed the true horizon. It is, if you like, the outermost hem of the black hole's influence, the place where space first begins to lose its footing and spin away into the dark. So the next time you picture a black hole, don't imagine it as a still, dark drain. Picture it turning, a smooth, silent, spinning thing, winding the fabric of space around itself, like a slow whirlpool in a midnight sea, described in full by just a few plain numbers, and yet dragging the very geometry of the cosmos into its endless, quiet turning. We have fallen a long way together. We've crossed the horizon, watched time bend and stretch, felt the slow turning of space, and now we approach the center of the black hole, the place toward which everything falls. And here, I have to be honest with you, in a way that scientists are not always comfortable being. Nobody truly knows what's there. Let me explain why. Because the not knowing is itself one of the most beautiful parts of the story. The mathematics that describes gravity so gracefully, Einstein's picture of space folding around mass, is astonishingly reliable. It has been tested again and again, and it has never once been caught making a mistake. And when you follow that mathematics all the way down into the center of a black hole, it gives a very definite answer. It says that all the matter that fell in, the entire heart of a giant star, and everything else that has ever tumbled past the horizon, is crushed down into a single point of zero size, a place where space is folded infinitely steeply, where the current of space plunges infinitely fast, where density becomes endless. Physicists call this point the singularity. But here's the trouble. Whenever the mathematics of physics starts producing infinities, infinite steepness, infinite density, a point of exactly zero size, it isn't announcing a discovery. It's waving a little white flag. It's the equation's way of saying, I have been pushed beyond the world I was built to describe. I can take you no further. An infinity, in physics, is almost always a sign, not that something truly becomes endless, but that our current understanding has run out. And this is where our two grand journeys, into the very small and the very large, finally meet. To understand the true center of a black hole, you would need to describe an enormous amount of matter crushed into an unimaginably tiny space. And to describe the very small, you need the rules of the quantum world, that shimmering realm of maybes and uncertainty we explored together last time. But to describe the very heavy, the steeply folded, you need Einstein's picture of gravity. And here is the great unfinished problem at the frontier of all physics. These two magnificent descriptions of reality, each flawless in its own domain, do not fit together. They contradict each other precisely where we need them most, at the singularity, deep inside a black hole, where the smallest scales and the strongest gravity collide. So when we ask, what is at the very center of a black hole, we are really asking one of the deepest open questions in all of science. It is almost certainly not a true point of infinite density. That's just the white flag, the equations telling us they've reached their edge. Something else must be there, something governed by a deeper set of rules we haven't yet discovered. Rules that would finally weave together the world of the very small and the world of the very large into a single, seamless cloth. Physicists have dreamed of this deeper theory for a century. They have given it names, and they have sketched beautiful, unproven guesses about what it might say. But the honest truth, the one worth resting on tonight, is that the center of a black hole is a genuine edge of human knowledge. It is one of the few places left in all the universe where we can point and say truthfully, we do not yet know. There's something I find deeply comforting in that, rather than frightening. We live in an age that often acts as though everything has already been figured out, as though all the mysteries have been solved and filed away. And yet here, hidden inside these dark folds in the sky, sits a question as open and unanswered as any our distant ancestors ever asked while gazing up at the stars. The center of a black hole is a reminder that the universe still keeps secrets, that wonder is not used up, and that somewhere out there, quietly waiting, are truths no human being has ever known. But even without knowing what lies at the very center, we have learned something astonishing about black holes from the outside, something that suggests they are not quite as black and not quite as eternal as they first appear. And for that, we turn to a man who reshaped how we think about the dark. For a long time, everyone assumed that a black hole was the ultimate one-way street. Things fell in, nothing came out, and there the story ended, forever. A black hole, it seemed, could only ever grow, swallowing more and more, never giving anything back, patient and permanent, until the end of time. Then, in the 1970s, a young physicist named Stephen Hawking asked a quietly radical question. He wondered what would happen if you took the strange rules of the very small, the quantum world, and applied them right at the edge of a black hole, at the event horizon. And what he found astonished even him. Black holes, he discovered, are not perfectly black after all. They glow ever so faintly, with the softest whisper of light and warmth. And because they glow, they very slowly leak away. Given enough time, a truly staggering amount of time, a black hole will actually evaporate, fading gently into nothing. To feel how this can be, we have to recall one of the strangest ideas from our journey into the very small. Empty space, it turns out, is not truly empty. Down at the tiniest scales, the vacuum is restless, faintly fizzing with activity as pairs of particles flicker briefly into being and then vanish again, borrowing a little energy from the universe and quietly paying it back a moment later. Everywhere, all the time, even in the deepest dark between the stars, this soft, invisible fizzing goes on. Usually it comes to nothing. The pairs appear and almost instantly find each other again and disappear, and the books are balanced. But now, imagine this fizzing happening right at the edge of a black hole, right at the horizon. Every so often, one of these fleeting pairs will pop into being just there, straddling the line, with one partner just outside the horizon and the other just inside. The one inside is swept away by the current, falling forever into the dark, unable to return to its partner. And the one outside, now suddenly alone with no partner to vanish back into, is left stranded in the wider universe. A real particle, drifting free. To a distant watcher, it looks as though the black hole has gently breathed out a tiny mote of light. Grain by grain, particle by particle, this is how a black hole glows, and each time it releases one of these escaped particles, it gives up a little of itself, a tiny sliver of its mass carried away into the night. The black hole, ever so slowly, grows lighter. It shrinks, it fades. Over unimaginable ages, it evaporates. Now, I want to be honest about the timescales here, because they are almost beyond comprehension, and there's a strange comfort in just how slow this is. For a black hole made from a collapsed star, this evaporation is breathtakingly gentle. So gentle that it would take vastly, absurdly longer than the entire current age of the universe for it to fade away. We're not talking billions of years or trillions. We're talking about a stretch of time so long that if you tried to write it out, it would be a 1 followed by so many zeros that the number has no everyday meaning at all. Long, long after the last stars have burned out and the sky has gone cold and dark, these black holes will still be there, sitting quietly, glowing almost imperceptibly, taking their unhurried time to disappear. In a sense, black holes may be among the very last things left in the universe. The final embers, glimmering faintly in an endless dark, outlasting nearly everything else that ever was. And smaller black holes evaporate faster, glowing more brightly as they shrink, so that at the very end of their lives, countless ages from now, they would finish not with a whimper, but with a final quiet flourish. There is something wonderfully poetic in all of this. The blackest objects in the universe are not truly black. The most permanent things we know of are not truly permanent. Even a black hole, that seeming symbol of the eternal and the inescapable, is quietly, patiently, over spans of time we can barely name, giving itself back to the cosmos, one faint glimmer at a time. But this gentle glowing opened up a puzzle so deep that physicists still argue about it today. A puzzle about what happens to everything that ever fell in. And that puzzle is where we drift next. Let's rest for a moment on a question that sounds simple, but which has troubled some of the finest minds in physics for half a century. When something falls into a black hole, and the black hole later evaporates away to nothing, where does everything that fell in actually go? At first, this might not seem like much of a puzzle. It fell in, the black hole faded away, and that's that, it's gone. But there's a subtle problem hiding here, and it strikes at something physicists hold very dear. One of the deepest principles in all of science is the quiet idea that information is never truly lost. Now, information here doesn't mean facts in a book. It means something more like the complete and total description of a thing, every detail of what it was made of, and exactly how its pieces were arranged. The principle says that, in an ideal world, you could always, in theory, run the film of the universe backward. If you knew the present in perfect and total detail, you could reconstruct the past and foresee the future. Nothing is ever completely erased. It's only ever scrambled, rearranged, hidden away. Burn a letter, and it certainly looks destroyed. But in principle, the information isn't gone. It's just scattered into the smoke and heat and ash, and a godlike accountant tracking every particle could piece it back together. Now here is the trouble. Drop that letter into a black hole instead, and then wait an unimaginably long time for the black hole to evaporate away by Hawking's gentle glow. When Hawking first worked out how that glow behaves, it seemed to carry no memory of what had fallen in. The particles trickling out looked utterly bland, utterly featureless, the same no matter what you had thrown in. A letter, a lump of iron, a dying star. It seemed to make no difference. The glow appeared to forget. And so, once the black hole had fully faded, the complete description of everything that ever fell in seemed to be simply, permanently, truly gone. Not scattered, not hidden, but erased from the universe altogether. That may not sound so terrible at bedtime, but to physicists it was almost unbearable, because it meant that one of their most trusted principles was being broken in the dark. Either black holes really do destroy information, in which case something we believed about the very foundations of reality is wrong, or they don't, and the information somehow escapes. And Hawking's original picture was missing something important. This tension has a name: the black hole information puzzle. And for decades, it set the world of physics gently at war with itself. I won't pretend to you that it's fully resolved, because it isn't. It remains one of the liveliest open questions at the frontier. But the tide of opinion has shifted, and most physicists now believe that the information does, in some subtle way, survive. The leading idea is that the glow escaping a black hole is not quite as featureless as it first appeared. Woven into it, in ways almost impossibly faint and scrambled, may be a hidden record of everything that ever fell in, the universe's own quiet insistence that nothing is ever truly forgotten. Exactly how this works, exactly how the memory is carried out through the glow, is something the cleverest people alive are still working to understand, with beautiful new ideas appearing even now. I find this a rather lovely thing to drift off on. The universe, it seems, may be deeply reluctant to forget. Even into the heart of the darkest, most devouring objects there are, even past the point of no return, some whisper of what once was may still, somehow, find its way back out into the light. Nothing, perhaps, is ever completely lost, only hidden for a very, very long time. But not all black holes are the star-sized kind we've been imagining. Some are so vast that our minds simply cannot hold them. So before we learn how we actually found these invisible things, let's take a moment to appreciate just how large the universe's black holes can grow. The black holes we've imagined falling into so far have been the star-sized kind, the collapsed hearts of dead giants, a few times heavier than our sun, their horizons only a few kilometers across. The universe is scattered with these. In our own galaxy alone, there are likely tens of millions of them, drifting silently between the stars, invisible unless something strays too near. But these are the small ones. The universe, it turns out, grows black holes on a scale that beggars the imagination. At the very center of almost every large galaxy, including our own, there sits a single black hole of a wholly different order. Not a few times the mass of the sun, but millions or even billions of times. Physicists call them supermassive black holes, and honestly, even that grand word feels too small for what they are. The one at the heart of our own galaxy, the Milky Way, has a name that sounds like a coordinate on an old star map: Sagittarius A star. It sits about 27,000 light-years away from us, quietly anchoring the whole slow, majestic spin of our galaxy. And it weighs about 4 million times as much as our sun. 4 million suns folded away into a single dark point at the center of everything, around which our entire galaxy, every star you have ever seen, including our own, slowly, endlessly turns. It has been sitting there, calm and patient, for the whole of human history, and unimaginably longer. And we never even knew it was there until the last few decades. And Sagittarius A star is, believe it or not, a fairly modest example. In a neighboring giant galaxy called Messier 87, there sits a black hole of some 6 billion times the mass of our sun, more than 1,000 times heavier than our own galaxy's central monster. Its event horizon is so vast that our entire solar system, the sun and all its planets, could tumble inside with room to spare, and you would hardly notice the crowd. And even that is not the largest. Out in the distant reaches of the universe, astronomers have found black holes so enormous that words begin to fail. One of the heaviest yet known sights at the heart of a blazing distant object called TON 618, and it weighs something like 40 billion times the mass of our Sun. 40 billion suns. A single object so heavy that its event horizon could swallow our entire solar system many times over. A dark heart larger across than the orbits of all our planets combined. It is difficult, lying here in the quiet, to truly hold a number like that in the mind. And perhaps it's better not to try, but simply to let the sheer scale of it wash over you, like the vastness of the sea. How do these giants grow so large? Over the enormous span of cosmic time, they feast and they merge. They draw in gas and dust and the occasional unlucky star, growing heavier with every meal. And when two galaxies drift together and slowly combine, as galaxies do, their central black holes eventually find each other and merge into one still greater black hole. Across billions of years, meal by meal and merger by merger, a black hole can grow from the corpse of a single star into a monster heavier than billions of suns. There's a strange and humbling comfort in knowing these giants are out there. They are not rushing toward us. They are not hunting. They simply sit, unimaginably far away, at the still centers of galaxies, holding the great pinwheels of stars in their slow gravitational embrace. Our own is one of them. That quiet 4 million sun heart around which our whole night sky turns. Everything you have ever looked up at and wondered about is, in the grandest sense, drifting in a slow, vast circle around the dark. But if these things are truly invisible, if not even light escapes them, then how could we possibly know any of this? How do you find something that gives off no light at all? That is perhaps the most wonderful part of the whole story, and it's where we go next. Here is the puzzle. A black hole gives off no light. It is, by its very nature, invisible, a dark patch against a dark sky. So how could anyone ever prove that these strange things are truly out there, and not just a beautiful idea scribbled in the mathematics? For a long time, we could only find them indirectly, by watching how nearby stars and glowing gas behaved as they swirled around something massive and unseen. But then, quite recently, we found a way to detect black holes directly, not by seeing them, but by feeling them, by feeling the whole universe shake. Cast your mind back to our very first idea tonight. That space is a kind of fabric, one that can bend and fold. Well, a fabric that can bend can also ripple. When something violent happens to a very massive object, when it moves or shakes with great force, it sends ripples spreading outward through the fabric of space itself, like the rings that spread across a still pond when a stone is dropped in. These ripples are called gravitational waves, and as they pass through, they very gently stretch and squeeze space itself, and everything sitting inside it. Now, one of the most violent events you could possibly imagine is two black holes crashing into each other. Picture it, far away and long ago, two black holes, born from two dead giant stars, caught in each other's gravity, circling one another. Over millions of years they spiral closer and closer, faster and faster, until in their final moments they are whirling around each other well over 100 times every second. And then they merge, two dark hearts becoming one, in a burst that briefly shakes the fabric of the entire universe. In that final instant, a black hole merger can pour out more raw power than all the stars in all the galaxies of the visible universe combined. And yet it releases almost none of it as light. It pours it out as a great shudder in space itself, a wave of pure gravity, spreading outward at the speed of light across the cosmos. And in the year 2015, for the very first time, we felt one. After decades of patient work, scientists had built an instrument of almost unbelievable delicacy, designed to feel the faint stretching and squeezing of space as one of these ripples rolled by. The challenge was staggering, because by the time such a ripple reaches us, having traveled clear across the universe, it is fantastically faint. The stretching it causes here on Earth is smaller than the width of a single atom, smaller, in fact, than a tiny fraction of the width of the particles inside an atom. To feel something that gentle is like measuring the distance to a faraway star and noticing it change by less than the width of a human hair. And yet, on a September morning in 2015, that instrument trembled. A ripple washed through the earth, through the ground, through the building, through the instrument, through the scientists themselves. A wave that had been traveling for well over 1 billion years, set off by 2 black holes, each around 30 times the mass of our Sun, merging in the deep and distant past. When scientists translated that ripple into sound, it made the softest little rising tone, a gentle chirp, lasting a fraction of a second. The sound, if you like, of 2 black holes becoming one, heard at last across more than 1 billion years. That single soft chirp was so important that it was honored 2 years later with the highest prize in science. Since that first trembling, we have felt many more, dozens upon dozens of these collisions, black holes and dead stars merging all across the sky, each one sending its gentle shudder rolling out to us. We have opened an entirely new sense, a way of feeling the universe that has nothing to do with light. For all of human history, we studied the heavens only with our eyes. Now, at last, we can also listen. And the universe, it turns out, is quietly ringing all the time, like a vast bell that has been struck again and again in the dark. But feeling a black hole is one thing. Actually seeing one, taking its photograph, sounds like it should be impossible. And yet, only a few years ago, we did exactly that. If a black hole gives off no light, then taking its picture sounds like a contradiction in terms. How do you photograph pure darkness against the black of space? And yet, in the spring of 2019, humanity did something that had long seemed impossible. We unveiled the first real image ever taken of a black hole. It is one of the great achievements of our age, and the way it was done is beautiful. The trick is that while a black hole itself is invisible, its surroundings need not be. Many black holes, especially the supermassive giants at the centers of galaxies, are wrapped in a swirling disk of superheated gas, spiraling inward like water circling a drain. As this gas whirls faster and faster and crowds closer to the horizon, it heats up ferociously and blazes with light. Some of the brightest, most energetic light in the whole universe. So a black hole is often ringed by a brilliant halo of glowing matter, and against that bright ring, the black hole itself appears as a dark round silhouette, a shadow. You cannot see the black hole, but you can see the hole it carves out of the light, the round patch of darkness where the glow suddenly stops because everything there has fallen beyond the point of no return. To capture such a shadow, though, you would need a telescope of impossible size. The black holes are so far away that photographing one is like trying to read the date on a small coin resting on the far side of a continent. No single telescope on Earth could ever be large enough. So astronomers did something wonderfully clever. They joined together a whole family of telescopes scattered across the entire planet, from mountaintops to high deserts to the ice at the bottom of the world, and linked them so precisely that they worked together as though they were fragments of a single telescope as wide as the Earth itself. It took a great collaboration of hundreds of scientists and mountains of data so vast it had to be carried around the world on stacks of hard drives and months upon months of painstaking assembly. And when at last the image emerged, there it was, a soft, glowing ring of orange light, and at its center, a round pool of perfect darkness, the shadow of a black hole. This first one belonged to the giant black hole at the heart of that distant galaxy, Messier 87, the 6 billion sun monster we met a little while ago, some 50-odd million light-years away. We were, in a very real sense, looking at the silhouette of the point of no return itself, a dark circle traced out against the glow of doomed infalling light. And a few years later, in 2022, the same team pulled off something even closer to home. They turned their Earth-sized eye toward the center of our own galaxy and captured the shadow of Sagittarius A star, our black hole, the quiet 4 million sun heart of the Milky Way. There it was, another glowing ring, another round patch of dark, this one belonging to the very object our entire night sky slowly turns around. After all those years of knowing it must be there, we finally saw its shadow with our own instruments. There is something almost dreamlike about those images when you really sit with them. For the whole of human history, black holes lived only in imagination and equations. Ideas so strange that even the scientists who first predicted them found them hard to believe. And now, hanging on the wall, there are photographs, actual pictures of the edge of the abyss, of the precise boundary beyond which everything falls and nothing returns. We took the single darkest, most secretive thing in all the universe, and we caught its portrait against the light. And these giant black holes are not lonely curiosities off in the distance. They are woven into the very structure of the galaxies, and into the story of how the universe came to look the way it does, including the great pinwheel of stars we call home. So as our slow night draws toward its close, let's rise up one last time, out past the horizon, past the swirling light, and see how these dark hearts help shape the grandest structures in the sky. We began tonight thinking of black holes as destroyers, cosmic pits that swallow everything and give nothing back. But the deeper we've fallen, the more that picture has softened. And now, near the end of our journey, we arrive at perhaps the most surprising truth of all. Black holes are not only destroyers. In a strange and profound way, they are also builders. They may be part of the very reason galaxies, and perhaps even we, are here at all. Remember that nearly every large galaxy has one of these supermassive black holes sitting at its center, holding it together. For a long time, astronomers assumed this was a mere curiosity, that the black hole just happened to be there, a heavy ornament at the middle of the galactic pinwheel, with little to do with the vast galaxy around it. But as they gathered more and more observations, they noticed something remarkable. The size of a galaxy's central black hole is closely tied to the properties of the whole enormous galaxy surrounding it. Bigger galaxies tend to have bigger central black holes, in a relationship far too neat to be a coincidence. The tiny, dark heart and the immense swirl of hundreds of billions of stars seem, somehow, to have grown up together, shaping one another across the long ages. How can something so comparatively small influence something so enormous? The answer lies in those brilliant disks of infalling gas we spoke of. When a supermassive black hole feeds, It does not swallow quietly. The gas swirling toward it heats up and blazes so fiercely and blasts out such tremendous winds and jets of energy that it can push the surrounding gas of an entire galaxy around. It can heat that gas and blow it outward, and in doing so, it can actually slow down or even halt the birth of new stars, since stars are born from cool, settling gas. So a galaxy's central black hole acts a little like a thermostat, or a slow cosmic heartbeat, gently regulating how quickly its galaxy forms new stars, and helping to keep the whole grand system in a kind of balance across billions of years. The destroyer, it turns out, is also a caretaker. This means the black hole at the heart of our own galaxy is not some distant, unrelated menace. It is woven into our story. The Milky Way we live in, the particular arrangement of stars and gas that eventually gave rise to our Sun and our Earth, and the slow chain of events that led to you lying here tonight. All of it unfolded in a galaxy shaped, in part, by the quiet influence of its central dark heart. We are not separate from these strange objects. In the grandest possible sense, we are their distant neighbors, and perhaps, in some small way, their children. And so the black hole, that supposed symbol of pure destruction, reveals its other face. Yes, it swallows. Yes, it hides an edge beyond which nothing returns, and a center we cannot yet understand. But it also anchors galaxies and shapes them, and helps set the gentle rhythms by which new stars are born. It is not simply an ending. It is part of the great, slow, endless cycle by which the universe builds and unbuilds and builds again. That, I think, is a rather beautiful note to carry with us towards sleep. The idea that even the darkest things in all creation have their quiet part to play in bringing forth the light. Before we let the night carry us off to sleep, let's indulge in one last dreamy question, the kind that has fired imaginations for generations, and that people always ask when black holes come up. If a black hole is a place where space folds so steeply that it pinches almost shut, could it perhaps be a tunnel, a doorway? Could you fall in one side of the universe and somehow come out somewhere else entirely, another place, another time, another cosmos altogether? It's a beautiful idea, and I want to be honest with you about it, because the honesty is part of what makes it lovely. When physicists follow their equations into and beyond the folds of an idealized black hole, they do sometimes find, on paper, strange bridges, theoretical tunnels linking one region of space to another far away. These have a wonderful name: wormholes. In the pure mathematics, in certain idealized cases, such tunnels can appear as though the deeply folded fabric of space had been pinched together until two distant points nearly touched, joined by a hidden shortcut through the dark. But, and this is the gentle, important but, as far as anyone can tell, these tunnels are almost certainly not something you could ever actually travel through. In the realistic black holes that nature makes, the ones born from collapsing stars, these bridges either don't truly form, or they would be so violently unstable that they'd pinch shut the very instant anything tried to pass, crushing any traveler long before they reach the far side. To hold such a tunnel open, physicists suspect you would need some exotic kind of material that may not even exist in the universe at all, a substance with properties so strange that, for now, it lives only in equations and dreams. So the honest answer is this: black holes are almost certainly not doorways. If you fell into a real one, you would not emerge, blinking, in some distant galaxy or bygone age, a ding. You would simply fall and stretch and join the great hidden mystery at the center that we spoke of earlier. The tunnels are a haunting hint tucked inside the mathematics, a whisper of what deeply folded space can do. But they are not, as best we understand it, an escape route or a road to anywhere. And yet, I don't think that should sadden us. There is something almost more wonderful in the truth than in the fantasy. We don't need imaginary doorways to distant worlds, because the real black holes are astonishing enough. They are places where space pours inward like a river, where time slows and freezes, where the brightest stars end their lives as invisible points, where the universe still hides secrets we cannot read, and where, even now, a faint glow leaks patiently out into the dark. The universe did not give us tidy tunnels to other worlds. It gave us something stranger and truer, real, genuine mysteries, sitting out there in the night sky, waiting quietly to be understood. And perhaps that's the most restful thought of all, that the cosmos is not a solved and finished thing, but a place still brimming with wonders, some of which no one has yet explained, and some of which are waiting, maybe, for minds not yet born. We've come a long way together tonight, you and I, all the way from the gentle inward drift of ordinary gravity, down across the point of no return, past frozen clocks and stretching light and slowly turning space, to the edge of a mystery even the wisest among us cannot yet explain. And now, as the night deepens and your thoughts grow soft and slow, let's gather it all up and set it gently down. A black hole, we've found, is not really a hole, and not really empty, and not really the devouring monster its fearsome name suggests. It is a place where a great deal of matter has folded space so steeply around itself that it has sealed off a small piece of the universe behind a one-way current. A quiet corner where light cannot climb back out, where time runs strange, and where the smallest and largest ideas in all of physics meet and tangle. Black holes are the dark corpses of brilliant stars. They anchor whole galaxies, including our own. They ring the cosmos like bells when they collide, and glow ever so faintly as they give themselves back to the night across spans of time we can barely name. And at their hearts, they keep a secret that no one, as yet, has ever read. If there's one soft thought to carry with you into sleep, let it be this. The things that seem the most frightening, the most final, the most impossibly dark, are so often, when we approach them slowly and with a little patience, revealed to be strange and intricate and even beautiful. The universe is under no obligation to be gentle with us, and yet, again and again, when we look closely at its most extreme and terrifying creations, we find not chaos, but a deep and quiet order, a cosmos that bends and folds according to elegant rules, keeping its mysteries not out of cruelty, but simply because we haven't quite finished learning how to read them yet. Thank you, from the bottom of my heart, for spending this quiet while with me, drifting toward the darkest and most wonderful places in the sky. Wherever you are in the world, and whatever tomorrow may hold, I hope you feel, just now, a little smaller and a little safer beneath this vast and patient universe. Rest easy. The stars will keep turning, slow and certain, all through the night. And the dark, as we've learned tonight, is nothing to fear. Sleep well.